Good morning, everyone. Let's get started with the session number 13 of this FSTA conference with a first talk entitled A Note on the Minimax Decomposition Integrals, and the speaker is Adam Saliga.
So I'm going to talk about minimax decomposition integrals. And since these are a modification of classical decomposition integrals, I'm going to give a quick introduction to decomposition integrals and what they are. So the idea of decomposition integral goes back to Evan and Lehrer that published the paper in 2014. We will consider only finite spaces, and these integrals are based on subdecompositions of functions. So the first thing, the functions are going from the space X to non-negative real numbers. The space of all such functions will be denoted by F, and we thus consider subdecompositions, which are written here. We are considering only non-negative subdecompositions, so the coefficients are greater or equal to 0, and the sets A cannot be arbitrary but are given. So we will consider only allowed sets. The allowed sets can be found in a collection. So collection defines the sets that we can use for the subdecompositions, and the set of collections or list of collections form a decomposition system. The class of all collections will be denoted by D, and the class of all decomposition systems will be denoted by H. So this is the introduction. And of course, we are integrating with respect to some monotone measure, which is going from the power set of X to non-negative real numbers, and the class of all monotone measures will be denoted by M. So what is a decomposition integral? So if we choose a decomposition system H, then we can define the following operator from the functions and monotone measures to non-negative real numbers, given by this formula. What happens here that for every collection D in the decomposition system, we assign this value, this suprema, which is obtained that for every subcollection of subdecomposition of F, we assign, or to every subdecomposition of F, we assign this value. So we change the indicator function by the value of the monotone measure, and we find the suprema of all possible subdecompositions in this sense. And we also take the suprema through the collections in the decomposition system. Some examples that are well known. We have, for example, the Shocked integral. If we consider all chains here, to obtain the Shocked integral, we can either consider all chains or all maximal chains. Here is an example of all maximal chains for the set for the space X consisting of two elements. We can also obtain the Shilkred integral if we consider all singleton collections in the decomposition system. All partitions lead to pan integral. We can also obtain the concave integral if we have only singleton decomposition system consisting of the maximal collection, and also, for example, a PC integral that was introduced by Andy and Professor Messier. So there's a bit complicated condition. So these are examples of decomposition integrals, and particularly collection integrals are part of decomposition integrals, and these are the decomposition integrals with respect to singleton decomposition systems. So we have only one collection. And since we have only one collection, we can denote it by D, and the collection integral will be denoted by this symbol here, COLD. An example of collection integral is the concave integral, which is with respect to the maximal collection. Interesting fact is that all decompositions can be expressed using the collection integrals, which is the main idea you will see in a second that leads to minimax decomposition integrals by the collection integrals. So we have that the decomposition integrals is just the suprema of collection integrals with respect to the collections contained in the decomposition system. So now let's define the minimax decomposition integrals. The main idea is to replace the outer maximum operator by the minimum operator, and why this is beneficial or why we should do that. So we want to be able to model some minimax problems. For example, we can minimize the potential maximal loss, which can be modeled by collections and decomposition integrals. So this is the definition of minimax decomposition integral. So if we choose a decomposition system H, we can define operator which represents minimax decomposition integrals using the formula. So we take the infima of the collection integrals here. So this is the definition. An example. So if we have, for example, set of workers, which is our space X, the function f can represent, for example, the working hours of individual workers. The monotone measure represents the productivity. And we have also working policy, which will be encoded by the decomposition system. So, for example, we can have that all workers start to work together and then they leave one by one. So this is contained in a decomposition system H that consists of all maximal chains on X. So in the case of classical decomposition integral, we would obtain the Shocked integral. But here we have the, we will find the minimal productivity of the setting. So this can be beneficial, for example, for in the setting for companies that they want to find what is the minimal productivity they can obtain, what is the maximal in the sense of classical decomposition integrals. So what are the properties of minimax decomposition integrals? The first property is that they are non-decreasing in both arguments. So this is classical property. This leads to the following, that they are an aggregation functions, no matter what monotone measure you choose, which is, again, they are positively homogeneous. So this is, again, a property also of decomposition integrals. They are continuous and piecewise linear. And one of the interesting properties of this integral is that they are superadditive. And examples, so here we obtain two different integrals, not as in the case of decomposition integrals where we obtain the Shocked integral for both the maximal chains and all chains. Here we have two different integrals. So for example, if H consists of all maximal chains, then we will obtain this integral. So it's just the minimum of the function scaled by the measure of the whole space. If we consider all chains, then we will obtain this formula. So it's the minimum of this product for each element of the space. If we have singleton, then we will obtain the classical decompositions integral. So if we have a maximal collection in the decomposition system, then we will have the concave integral. And for example, if H consists of all partitions, we will obtain this formula here. So these are the examples of minimax decomposition integrals. We can also introduce a new preorder on the class of decomposition systems by the following. If we take two decomposition systems, we say that the first one is less or equal to the second one if and only if for every collection from the bigger decomposition system, we can find a sub-collection in the smaller decomposition system. So this is written here. This is the other way around than in the case of decomposition integrals, where we have the order or this pre-order in the sense that for every smaller one, we can find a greater one in the larger decomposition system. And this allows us to order also decomposition integrals using this pre-order. So if we have two decomposition systems, such that the first one is less or equal to the second one, then also this inequality sign is satisfied by the decomposition, the minimax decomposition integrals. So this is an example. Also, we can work on alternative using to define maximum decomposition integrals. In this case, we are working with super decomposition integrals. So super decomposition integrals are defined again on the functions and monotone measures, but there's a little difference. In this, you can also obtain the infinity as possible value of this integral, and it's the minimum through the collection of the minimum of super decompositions of the functions. So we have this inequality, and the infinity is obtained when this set is empty. So that's why it can attain infinity. We can also express this by super collection integrals. So super collection integral is this part here for collection D. So we take the minima of the super collection integrals. And again, maximum decomposition integrals are obtained by replacing the outer minimum by the maximum. So this is some uh, example of use which can be modeled by maximum integrals, and this is the definition. So we take the suprema of super collection integrals. So we change this operator to maximum. Since we can attain a value of infinity, we have the following theorem. Which states that the infinities can be that the maximum integral is always less than infinity, so it's a real valued number, if and only if for every collection D there exists some sets AI such that the index I is the element of this set for every index from the space. In the following, meaning in the properties of these maximum decomposition integrals, we will use that they are always less than infinity. So they are again non-decreasing, they are aggregation functions, they are positively homogeneous, they are continuous piecewise linear operator, again in the case that they attain no value of infinity, and they are subadditive. And the last thing is that the preorder and maximum decomposition integrals are related in the following way. So if we have two decomposition systems such that the first one is less or equal to the second one, then the inequality sign is reversed in the case of maximum decomposition integrals. In the future, we want to replace the outer maximum minimum operators by some general operators and see what properties can be maintained, and also find applications of these results. So thank you very much for your attention.
Thank you. There is some questions or comments? No? Perhaps I could ask a question. I'm not an expert, but there are a lot of integrals. So what is the characteristic that is more characteristic of this type of integrals?
So the main idea of the decomposition integrals is that they are a general framework which contain many of the well-known and used integrals. So they cover a big class of integrals that are used in practice. So this is just a way to expand this class based on this idea of letter and
like a general study.
yeah.
Okay. And for the application, you have some idea in mind, or
Yes, in mind.
and you keep it in mind?
We are working on that.
Okay.
So
Okay. Some other question? No? So let's thank the speaker again.
yeah.
Yeah, yeah. So the next speaker, yeah. So the next speaker, I was waiting for that, is Barbara Pecada, and she will be presenting a presentation on titled Methods of Aggregation Process in Federated Learning Model.
Thank you. I would like to talk about some methods of aggregation used in federated learning models in the field of medical diagnosis, especially, and why medical aspect interests us, because in many because collecting large amounts of data in some medical centers is difficult often, and then with a small or unbalanced data sets is hard to generate sufficiently universal model. And what is problem? Because these medical centers do not want to share data to the others because of data privacy, lack of patient authorization, or similar problem. And moreover, then some medical centers have imprecise or incomplete data. And in this situation, very good idea help us federated learning models, which which idea is to share not data but learned local models and share only parameters of these models, which after aggregation was returned to individual units, and of course after many repetition, we obtained more effectiveness models for each local, for each clients with maximum data privacy. And so we concentrate and we want to propose a federated learning method that can handle uncertained and in the same time unbalanced data. And we use interval valued fuzzy set theorem to good representation of uncertainty. And we we want to improve the performance of our local models using different aggregation method, fusion, and we compare effectiveness for this aggregation method. And firstly, I recall some some main kind of federated learning models. We have horizontal federated learning, which characterize this aspect that we have in each local models the same attributes for our data, and and we have different data set. So different, for example, people, different clients, etc. But in the second kind of federated learning, we have dually. We have we study the same group of people, but on each part, on each local models, we have different attributes. Is considered different real problem. For example, some shop or some medical center, etc. Of course, we have also hybrid methods, but I concentrate here on the first horizontal models, when we have, how I say earlier, different local. I'm sorry. Different local models with where we have different data sets with the same attributes, characterize the same attributes, and for each we use the same machine learning algorithm to learn. Effectiveness we check for each of these models, and parameters of this learning algorithm we send to the server, where after aggregation are returned to each, and we check results to our decision making. And so this I explained earlier. Maybe I say it only only that we stopped in a situation where we obtain enough high effectiveness of our models, or we see not possible to improve them, for example, or for example, if we assume some number of iteration to learn in our aspect also. So we study different scenarios. And only a short recall, interval valued fuzzy set is used for us to good representation of uncertainty. So each attributes, each values is represented by interval with two fuzzy values. Where we, for this structure of data, we can of course use interval valued fuzzy aggregation function, which we know, and we also use in our models some operations of Moore arithmetic, sum and product especially, so which we see here, and also very helpful for us will be a representation introduced by Piegat 2014 to calculation some values of assumed to the interval by some parameters. And now we go to the main our result, because I said that we will compare some effectiveness of use different aggregation, because in first models was only used arithmetic standard arithmetic mean to aggregation for studied for different learning models, but usually was used this aggregation. And we with our team we study different aggregation, especially we compare with this arithmetic mean results for Sugeno and Choquette. Here will be present. And both of these integrals are based on the fuzzy measure. So I recall here only definition. And later I explain more how we calculate, how we use for Sugeno and Choquette integral, both basic elements for this definition. For example, for fuzzy measure, we will take information about efficiency of local models, and second values will be connected with our parameters which we have in our models. And Choquette integral are based on the same elements, but of course instead of maximum and minimum we have sum and difference which we see here. And we trained after in our assumed number of iterations and our models, and we calculate and we find trained parameters called here by B. And this vector of parameters was aggregated in server, so which we need to proposition of some decision making, some decision where we calculate based on these parameters and input attributes, input values for each object. And here we see modified by us federated learning model where we assume that next to the parameters we also send some aggregations because we send to server both of this information, and after validation also we check effectiveness. And after aggregation, based on the parameters and effectiveness of each models, we obtain new values of these parameters. And So here we see that we will send to servers the following effectiveness parameters, and finally we will see results for arithmetic mean and Sugeno and Choquette integral as to compare of results of this. And here we see how we calculate this fuzzy measure, especially based on quality values. Here we only observed accuracy and AUC, but we check more, of course, and parameters, of course, will be included to calculation of Sugeno and Choquette. And we use to learning model algorithm to learn logical regression, because we think that it is optimal for medical data where we have dual two values for decision, 0 and 1, and in process of learning we use gradient and error, which we have presented here. And our data are connected with breast cancer from the repository USC. Here is source, and for each attribute we build intervals in the following way, where because we have for each values mean and standard deviation such information, and by this we normalize earlier, and in this method we build interval representation. And to check how to creation of federated model, we prepare three clients. We randomly divided into our data to three parts, and in the first step we divide by balance decision for each, but we also will be a check, of course, for two of these three clients unbalanced behavior, and we will observe our results of using federated model. And our scenarios are following for experiments. Firstly, we check for centralized data, for all data. So we have benchmark model, we called. And next, in the second scenario, we check for local models after the division. When we have three parts of our data, and we check effectiveness for each separately, without federation, firstly, but also with aspect balanced and unbalanced data. And the third and fourth scenarios are connected with federation, where in third we use for aggregation arithmetic mean, which is now from many papers presented earlier, and we study in the last scenario Sugeno and Choquette to compare. And in benchmark model, we see that our data have the following effectiveness. For accuracy, for example, we have this very high level. And what we see for second and third scenarios, for local models, for local models, only firstly we study only for balanced data. For each local models we have balanced data with respect to a decision, and we see that we see some worse results, but very similar all without federation and with federation when we use arithmetic mean. So not spectacular results, but if we see Sugeno and more Choquette integral, then we obtain very high results for what we see, for example, for accuracy. But we have only balanced data for each. And now we will see what happens when we use unbalanced data, and we prepare this unbalanced situation when we for second clients we use 70 first decision dominates, and opposite for third. The second decision is dominates. So we have, of course, we study different scenarios for this unbalanced, but we obtained always similar situations. So here we concentrate on this, and what we see for unbalanced data, of course, is very low level of effectiveness for these local models with unbalanced data. It's better for when we use federated learning model with arithmetic mean to aggregation method. But what we see for Sugeno and Choquette, we obtain the same very high level for Choquette when we have unbalanced data. So we obtain the same level to data balance. So it is a very success for us, and so we may conclude that Choquette is very good for this data. Of course, we study only we concentrate now on medical data. So we will in future want to study different areas from real problems to check for our methodology. And of course, we want to study also vertical federated learning model, which is very important in many practical problems. And especially, we want to use some consumer quality weights connected not only with effectiveness model, what we see now, but more. We want to obtain more aspect, economic, financial impact of the informant, because sometimes very good local models not want to use be included to federation because don't have some positive aspect. So we must calculate some proposition for this situation, some gifts for example, because of course only the worst model obtained progress for their in this federated learning model. So thank you very much.
Thank you for a nice presentation. There are questions, comments? Yes.
So first of all, thank you for your presentation. Currently, I'm working on a similar problem. It's a little bit different. I'm not so concerned about the ownership of the data, but rather that I have millions and millions of data. So I'm working on a system that is similar to yours, what you have proposed. I have the data separated in different machines, and they train the same model locally as yours, and they are combined. Your results are mainly about performance when it comes to the classification or so on. But I'm more concerned about what it's time efficiency, because my model takes a lot of time. So have you checked if the generalization with the Sugeno and the Choquette are more, let's say, faster, or there is a difference in performance rather than using the main and that I'm currently using, for example?
You ask if it's faster?
Yeah.
We have similar results. We of course we must use Java, because in Python, for example, was very slowly, and we have problem obtained for for example, for the 100 iteration in a positive aspect results, but in Java was okay.
Okay, thank you very much.
Any other question? No? So let's thank the speaker again. And the next presentation will be done by Mirko Navarra, and the title is Uniqueness of Generator is What We Need.
Ladies and gentlemen, I will speak of a topic which requires good motivation, and don't be afraid that after last evening you will be too tired, because it will be full of pictures and very few formulas. So I hope that you can cope with that. I hope I could move. Yes. So inspiration. If you are given a function, you can estimate what is the shape of its derivative or integral. So you see, okay, the derivative is 0, then it's it's negative. Here it comes to 0 again and it grows. You would recognize this is not the integral. The integral must be now negative, 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 now increasing, still negative. Okay, better this way. Yes, these are the correct ones. So here you have an intuition. You would know which figure shows which feature. Now we can switch. This is the
Yeah.
Okay, thank you. And now, what about binary functions? Oh, sorry, not the right direction. Associative binary operations, which means T norms, associative couplers as typical examples, they overlap, yes. And the problem is that we do not see associativity on the graph of a binary function. This is replaced by the trick that we switch to some known associative operations like addition and multiplication. And that's an observation made already by Abel 200 years ago. Many associative operations are just translations of addition or multiplication by some nonlinear change of scale on a proper domain. So we have additive generators and multiplicative generators, which transform this associative operation to addition or multiplication. And now, recall that these are determined here in this context. They are of this shape, decreasing additive generators, increasing multiplicative generators, decreasing additive generators can be unbounded, multiplicative are bounded by the unit interval. And they are not uniquely determined by the binary operations. The additive generators are determined up to positive multiples. Not such a big problem, because you see that it's the same shape, just dilated in the vertical dimension. Well, the multiplicative generators are determined up to positive powers. We do not have such big good feeling of recognizing powers. So what happens? Task for you. I dare to ask you, yes? You have two T norms here. They are different. You see here near 0, 0, near the origin, there is some difference. The question is, which of the following generators, multiplicative generators, correspond to which of these T norms? Would you guess? Okay. We have magicians here. I can tell. Possibly. Yeah. Well, what? The middle? The middle is what? Right or right? Okay. And what they ask? Okay, yes. You may toss a coin. You have 32 possibilities. So if you give random answers, there is a big hope that somebody will guess properly. Okay. Now, what are these? These all are multiplicative generators. Which corresponds to which of them? This is the answer. Only this one is exceptionally related to the right one. The others are to the left. Yes, you were right, but you gave just one bit of the answers, and 5 bits were expected. Okay, what is the difference of this and the other shapes? If this is irrelevant, that's all the same. Why this is not the same? That's the question. And we tried to investigate it in more detail. So, in order to speak of the shape of a generator, we may need to say something. For instance, you may ask whether the generator is convex. There are many results of Ghizali-Ricci and Fodor about tenons with convex additive generators. Okay, convexity of an additive generator is not a problem because it's preserved by the multiplication. Convexity of the multiplicative generator, there is nothing like that because when you switch to another one, you lose it. So it doesn't make sense. So now, for instance, so we want to choose one specific generator and speak of that as a starting point for saying anything about its shape and convexity and so on. So let's look at Frank Tenoms. The generic formula, I mean, what you find in the books, if you draw it, you get these additive generators and these multiplicative generators. Okay. In order to have them unique, let's fix their value at one point. Any point, say 1/2, but you can say anything else. You can fix it to be exactly to have the same value. And now you see the order of the generators reverted. Well, so big trouble, but a bit surprising. Here we cannot say that they are ordered. The change of shape is strange. And why to choose exactly 1/2 and not anything else? So there is no privileged value to fix it. So let's look for some other solution. So let's fix it. Okay, so the question is at which internal point we do it. And now an example of a nilpotent family of tenoms, Jaeger tenoms, and you see, okay, the generic form is like this. Multiplicative generators. If you fix it at one point, oh, that's ugly. Okay, we probably do not want to compare these shapes in the family. It was better before, maybe. So let's look for alternatives. Yes, fix a value at an endpoint. That's some distinguished point where which we have chosen. Okay, that's a good. In fact, in the case of Jaeger tenoms, we already had it. We had it fixed at the beginning at 0, and that looks reasonably nice. Yes. The bad news is that this works for nilpotent tenoms, where the value at 0 for the additive generator is finite. If not, for strict tenoms, you have infinity. So don't fix it and There is no help. And for multiplicative generators, you get 0, again, nothing. So for nilpotent t-norms, we have some reasonably satisfactory answer, but for the strict ones, okay, it failed. There's nothing like, okay, you may say, let's fix it at the other end. No help. Yes, because these are already fixed and known. It doesn't say anything. So let's go on. What about fixing the derivative? At an end point, okay, fixing the derivative in some interior point would be really strange. Let's take the generators which have this tangent, the slope of the tangent. Forget it. So, but at the end, and that gives reasonable pictures for Frank t-norms. The generic form is this one. If we fix the derivative at 1, we give this nice picture, which says, okay, well, depending on the parameter, we go from this to this. Again, notice that the order was interchanged. Yes. For multiplicative generators, which were of this form, it means, okay, look at the derivative at 1, adjust it so that it will be a fixed value. You get this. You may like it, you may not. Okay, that is some reasonable solution of our task, how to choose unique generators for any t-norm in this family. The other idea is fix the derivative at 0. Well, as we have to think. For nilpotent t-norms, and additive generators, that helps. But it's not very nice result. Again, having the same slope but different volume. Right. For strict t-norms, it's minus infinity. Bad news. Not usable. For multiplicative generators, very often the derivative at 0 is 0. You cannot divide. Or infinity, also bad. Sometimes it's not the case. So sometimes there exists a multiplicative generator with a derivative at 0, non-zero and finite, so that we can normalize by dividing by by changing this by this value. Okay, we call it balance generator. It's a special multiplicative generator which has nice derivative at 0. If it exists, it's at most 1. For some strict t-norms do not have it, and if they have it, that's just 1. For any other generator, we fall in one of these degenerated cases. So let's use the balance generator. Now an important news. Now you cannot choose what the derivative at 0 should be. It's unique. It's uniquely determined by the t-norm. And you cannot say, I want to have it 1. No, it's something. Be lucky that it's not 0 and not infinity, and don't ask for anything more. And the question is, how can we find it? And we found a procedure. Let's take any multiplicative generator, compute this limit. If this limit happens to be non-zero and finite, use it as an exponent which transforms the original multiplicative generator to another one, and this will be balanced. So there is a procedure how to find the balanced generator if it exists. Example. Again, example. So there are some generators of t-norms of strict T norms. This is the generic form. If we transform them to balance generators using the previous procedure, okay, using this formula, we get such a picture. Okay, these are the balance generators. The derivatives at 0 are not the same. They go through some scale. Another example, Frank T norms have generic multiplicative generators which are already balanced. They have non-zero finite derivatives, different ones. Yes. So this, as you take them from the literature, Clement, Messier, Pape, are balanced generators. So they do have them. And now something about copulas, associative copulas with balanced generators. We can compute the density near the origin. It's the second mixed derivative, its limit at the origin. Here, the derivative reduces to this formula. It's simply the proportion of the values of the T norm and the product T. And this is exactly that magical non-zero finite derivative of the balanced generator at 0. So the conclusion is that in the vicinity of the origin, you may approximate such a T norm by a product multiplied by a constant. Not a surprise if the constant is less than 1. Yes, you can imagine it. The constant can be arbitrarily great. Yes, this can be a big number, 1,000. Still, you can approximate it by a product multiplied by 1,000, which is, of course, more than allowed. But in the neighborhood of 0, it is in the Fresher-Höfding bounds. So it can be. Locally, it is a multiple of a product. This is an important consequence, really important even for your money bag. Yes, because in financial models, they model upper and lower tail dependencies, and they are 0, which means in this region, we have asymptotically no dependence. What does it mean? If you try to estimate the probability that two random variables achieve extremely low values, your model considers them like independent, which is really bad. The crisis in 2008 was caused by this ignorance. Yes. So you may say, why do we study such bad operations? Because they are T norms and they are used in many other fields. So why not? Don't use it for models and banks, but continue. Feel free to use it in fuzzy systems and so on. And the balance generator can be very often found at the limit of this expression, which means look at the T norm, which values it achieves for small one argument taking a small constant. Scale it back to so that the range is between 0 and 1, exactly. And what you get is a very good approximation. In the limit, it's the same. So you see here, we use not very small argument, just 1/10, and already you can hardly recognize Last question for you. And now, again, the same T norms. Their balance generators are below. Which of them fits to which of them? Now, just one bit is to be answered. Your guess? Aligned? Crossed? Show. Aligned? Mixed? Swapped? Who is? You don't have an opinion? You should have. After this, they are swapped. Look at this place. Yes, yes. Here you see the shape. This is convex. This is concave. It must be swapped. Thank you for your attention. Yes.
Thank you very much. We are running out of time, but if someone has some quick question. Actually, I have a question. You think that by studying this type of generator would help to study the problem between the relation of the expression of the norm and the generator? Because as far as I know, if you have the generator, you can, of course, obtain the expression of the norm, but the other way around, if you have the expression of the norm to retrieve the generator, is not that straightforward. You think this study will help in this problem?
Well, this story was preceded the work which I presented, and this is one of the tools. This is one of the tools which tells you, given T norm, here you find the generator. And we have developed several other formulas, but they determine just the derivative of the generator, so they are not so much visible, so easy. So this is one of the collection of results of the direction, and they do not cover all cases, but they do cover all strict T norms which we found in the literature. So for any door which we found, which we encountered, we found a key. But we know that we do not have keys for all doors. Yes. Thank you for the suggestion of possible extension, future extension. By the way, my co-author, Kamila Hušková, continues work on that. Good idea.
Let's send the speaker again. And the last talk of this session will be done by Jana Bolsova, and it's entitled Socket Integral on a Hyperspace.
Okay.
Dear participants, to begin with, let me introduce two papers. In the first one, the authors looked at some methods for transforming measures to the power set. They proposed an approach how to transform measure μ, which is defined on the power set of the basic set X, to a measure μ with hat, which is defined on the power set of the basic set X. Therefore, μ with hat assigns values to collections of subsets of the basic set X. In the second paper, the authors introduced a new concept of the so-called generalized survival function. They generalized the standard survival function, and they generalized a concept of the Socket integral using this concept, the generalized survival function. Observe that the usual form of the standard survival function may be rewrite as follows. And the authors generalize the survival function by replacing the supremum of the function by some functional, which is called conditional aggregation operator. The conditional aggregation operator assigns a new value to a function f on a conditional set. Therefore, the value of the conditional aggregation operator depends on a conditional set. Inspired by results in the first paper, we proposed a transformation of one monotone measure space to the other, and we showed that the generalized survival function and the generalized Schucker integral may be seen as a standard survival function and standard Schucker integral on a hyperspace. Our approach has some advantages as a means of studying the properties, as we shall show. So let me recall a basic concept of our study. It's a family of conditional aggregation operators. We need a collection of subsets of the basic set X such that X belongs to it. Further, let G denote a family of non-negative real-valued functions containing indicator functions of all sets in the collection. Then a family of conditional aggregation operators is defined as you can see. This A denotes the conditional aggregation operator which satisfies two conditions. The first condition requires the monotonicity of the conditional aggregation operator on a conditional set. And the second property reflects the fact that zero-valued data on a conditional set doesn't change the value of the conditional aggregation operator. As we can see, the empty set isn't included in this definition. It's because the empty set doesn't give us any additional information for aggregation. But if X belongs to the collection, here in a family, we get A on the empty set. Naturally, we set it equal to 0. Typical examples of families of conditional aggregation operators are supremum family, which contains supremum conditional aggregation operators. They are nothing but supremums of functions on a conditional set. Further, similarly, infimum family, or if we consider countable, the basic set X, then we can consider some family of conditional aggregation operators. Of course, we can consider a family of Schocket, Sugeno, and Schilkert integrals. Therefore, conditional aggregation operators cover many existing aggregations used in the applications. What is important that a family of conditional aggregation operators doesn't have to contain elements of only one type. For example, we can consider a family which contains supremums, conditional aggregation operators on some sets, and infimum, conditional aggregation operators on other. As I mentioned in the introduction, we have introduced a transformation of a monotone set function to a power set. Let me note that we use the term monotone set function instead of the term monotone measure because we require μ to be defined on any collection of subsets of the basic set X. Even the empty set doesn't have to belong to it. Therefore, we defined a transformed monotone set function and as we can see. And μ is tied with a monotone set function μ and is defined on the power set of the collection of the basic set X not only on a subset of the power set of the basic set X. Therefore, NME measures families of sets. For a better clarification of NME, let me give an easy example. Let us consider monotone measure, monotone set function me, which takes finitely many values from U1 to UQ. Then me also takes finitely many values from U1 to UQ, and in the particular, it takes the value Uj if the measured family of sets doesn't contain a set of measure Uj and contains all sets of measure less than Uj. And me takes the greatest value UQ if the measured family of sets corresponds to the input collection. As I mentioned, we try to show that the generalized Schoke integral is a standard Schoke integral on a hyperspace, and we tried it to show via NME. So we studied the properties of NME. These properties directly follow from the definition of NME. So NME is a minitive monotone set function and supermodular, superadditive, and upper semi-continuous. If we consider the collection containing the empty set and the basic set X, then NME is sigma additive if and only if me is the greatest capacity. Further, NME vanishes if and only if the measured family of sets doesn't contain a set of measure 0. The range of NME is equal to the range of me, and NME of the input collection is equal to me of the basic set X. So, transformation of a monotone set function me to monotone set function NME is a basic idea of our study. We used it to rewrite the original formula of the generalized survival function, but except of monotone set function NME, we need a transformed set function T, which is defined by means of the conditional aggregation operator. So if we take NME and T, then we can rewrite the original formula of the generalized survival function as we can see. As we can see, we do alpha cuts of a set function T, and for better clarification, we can look at the scheme of the transformation of the input function f and the monotone set function me to hyperspace. Generalized survival function naturally gives rise to a generalized Schoke integral, but using our representation via NME and T, we showed that the generalized Schoke integral is a standard Schoke integral, but on a hyperspace. Therefore, it's a Schoke integral of a set function T and monotone set function NME on a family of sets. So as we know this, if we take finite collection of power set of the basic set X, then we can easily derive some computational formulas for the generalized Schoke integral. But compared to the original case, when we permute the input vector X, now we have to permute the input values of the conditional aggregation operators. We provided well-known formulas for the standard Schoke integral. So we covered well-known formulas, and we also used the standard Möbius transform to monotone set function NME, and we obtained the formula for generalized Schocker integral in terms of the Möbius transform. An example of the generalized Schocker integral, well known from the literature, is also the twofold integral. It was introduced by Narukawa and Tora. The authors took two pairs of operations, sum and the product used in the Schocker integral, and minimum and maximum using the Sugeno integral, and two different measures, μc and μs. We showed that this integral is a case of the generalized Schocker integral. It's enough to take the collection, which is a chain generated by a non-decreasing permutation of the input function f. And further, we need a minitive set function. This is tied with the input monotone set function μc. And further, we need a family of conditional aggregation operators. Now, the role of a transformed set function T is played by the Sugeno integral. But we need Sugeno integrals with respect to another measure. So we compute Sugeno integral with respect to another measure on each set from the collection. These measures are denoted by mi and are related to the input measure μs, as you can see. And presenting the Schocker integral as a standard Schocker integral on the hyperspace have some advantages as a means of studying its properties. These properties are easily derived from the standard Schocker integral. For example, the first one follows from the continuity of above of monotone set function μ. The second one follows from the supermodularity of NME. The third follows from the fact that NME is NME is additive if and only if μ is the greatest capacity, and so on. So we expect that our approach will yield some interesting results in the future. Thank you.
Thank you very much. Someone has questions, suggestions? No? Okay, perhaps I can do a question, although I'm no expert. So which one of the properties you studied you think would be the more characteristic one of this integral, or the more interesting to study?
Interesting. It was interesting that NME is a minitive monotone set function, and from minitivity follow some properties. So I think this is very helpful in studying other properties.
Okay, so some other question? No? Okay, so let's thank the speaker again. And this was the last talk, so we close the session. Good lunch to everyone.